Hello, I'm Tana, your MLC tutor. Alright, in this video I'm going to talk about how the Poisson distribution is related to the exponential distribution. For example, if the number of events or occurrences follows a Poisson distribution or is a Poisson process, then the time until the next event or occurrence follows an exponential distribution. So I'm just going to show you why that's true and why it makes sense. At least for me, that sort of helps me sometimes in the problem see what I need to do. So let's say, for example, the number of events, I'll call it n, follows a Poisson distribution with parameter lambda. So that will be the mean number of events or the rate at which events occur. And let's call T1, T sub 1 will be the time until the first event. Okay, so just based on this, we know some things about the time until the first event. Like, let's say, for example, we wanted to talk about the probability that the time until the first event is greater than some value. So, draw a little timeline. This is time 0, 1, 2, all the way up to, say, x. And I want to know the probability that the time until the first event is greater than x. So somewhere over there. The probability that time until the first event is greater than x. We know that this is the survival distribution. The probability that the time until the first event is greater than x. So if the first event happens after x, we know that there were no events on this interval from 0 to x. So this is the same thing as the probability of no events, or n equals 0, we'll say before x, or on the interval from 0 to x. Could have written it like that. So we should recognize this as the survival function for t sub 1, or the time until the first event. Evaluated at x. Okay, we said that this is the probability of no events happening on this interval. Okay, so our events occur at the rate of lambda. We know that the probability of a certain number of events occurring, if that number of events follows the Poisson distribution, is lambda to the k, e to the negative lambda over k factorial. So the probability of 0 events occurring simplifies down to e to the negative lambda. Okay, but lambda doesn't always have to be constant, or in other words, it doesn't always have to be homogeneous. It could be non-homogeneous, which just means that it's not constant, it's changing. The number of events that occur it varies with time. So often this is called the intensity function. This is the rate at which events occur varies with time, so it's a function of t. And the mean number of events that occur over some time interval, you get that by integrating the intensity function over your time interval. So our interval here is 0 to x. I'm going to integrate that from 0 to x. And it's easiest to see that you can already kind of see that this looks like the survival function for an exponential distribution, which, by the way, is e to the negative x over theta, where theta is your mean, it's easiest to see that this represents the survival function for an exponential distribution if you look at the case where lambda is homogeneous or constant, because then this simplifies down to e to the negative lambda x. So that would just be an exponential distribution where theta is 1 over lambda. If you plugged in 1 over lambda here, you would get this e to the negative lambda x. So we can see that the time until the first event follows an exponential distribution with the mean theta equal to 1 over lambda, where lambda is your rate at which the events occur. And again, we can see that the time until the first event is exponentially distributed because we found the survival function for the time, the random variable representing the time until the first event, and that equals the survival function for an exponential distribution. Okay, so I'm going to go through a couple of very short examples to show why this is useful to know how the time until the next event is distributed, that it has an exponential distribution. So this is an example out of my study manual, my ASM study manual. They say that the number of claims per day follows a Poisson distribution with lambda, or the rate at which events occur, equal to 4. So you expect to have about 4 claims per day. And we want to know the variance of the time between claims. So let's say that t is the time between claims. Now we said that if the number of events that occur in a given time interval per day, per week, per year, if those follow a Poisson distribution with mean lambda, then the time until the next event follows an exponential distribution with mean theta equal to 1 over lambda. And the exponential distribution is memoryless. So the time until the first event, the time until the next event, the time between events, you're standing at time 2, the probability of, this amount of time until the next event, it all is going to have, it's going to be distributed the same way with the same mean. You can forget past, it's memoryless. So our time between claims is going to follow an exponential distribution with mean theta equal to 1 over lambda, which is 4, so 1 over 4. We just want to know the variance of the time between the claims. I know that the variance of an exponential distribution is theta squared, so the variance of time between claims will be 1 over 4 squared, which is 1 over 16. That's it. So that one was very simple. This one is just slightly more complicated. This is another problem out of my ASM study manual. It says that claims arrive in a homogeneous Poisson process. So again, homogeneous sounds daunting, I guess, but it just means that your lambda, or the rate at which events occur, is constant. So claims arrive in a homogeneous Poisson process. The probability that the waiting time until the next claim, okay, so we know some things about how the time until the next claim is distributed. The probability that the waiting time until the next claim will be at least 2 years is 0.6. We want to determine the probability that exactly 4 claims will occur within 5 years. So let's just first start with that first part, the probability that the waiting time until the next claim will be at least 2 years. I'm going to, again, call the time until the next claim t. Now they said that claims follow a homogeneous Poisson process. They didn't give us the parameter, but it's some lambda. So I know that the time until the next claim is exponentially distributed with mean theta equal to 1 over lambda. The probability that the waiting time until the next claim will be at least 2 years, so the probability that t is greater than 2, they say is 0.6. Okay, I know that t is exponentially distributed. I know that the probability that t is greater than 2 represents the survival function evaluated at 2. So this is the same thing as survival function for t evaluated at 2. Since t is distributed exponentially, this is going to be e to the negative x over our mean, which is 1 over lambda, equals 0.6. We know that our x, which is just whatever we're evaluating it at, we're evaluating it at 2. So e to the negative 2 over 1 over lambda is 0.6. Then you can solve for lambda, and I got 0.2554. Okay, so that's per year. We found the rate at which claims occur in a year. We expect about 0.2554 per year. Now we want the probability that exactly 4 claims will occur within 5 years. So this is per year. Our lambda then for 5 years, or the number that we expect to see in 5 years, is going to be 5 times that, which is 1.2771. So this would be the number of claims in 5 years follows a Poisson distribution with that parameter. And I just want to know the probability that there are 4 claims in that period of 5 years. So probability of seeing 4 claims will be, let's see, lambda 1.2771 to the 4th times e to the negative lambda over 4 factorial. And I got 0.0309. And that's it. If you have any questions about time until next event or anything else, let me know. Happy studying.